This video is hypothesis testing of paired data part 2. We're picking up with example 4, cholesterol. A study was conducted to investigate how effective a new diet was in lowering cholesterol. Results for the randomly selected subjects are shown in the table. The differences have a normal distribution. Are the subjects' cholesterol levels lower on average after the diet? So, since we've actually gone through several examples, three examples on this already in the previous video, why don't you hit pause and try this one yourself and then come back and see how you did. So we're trying to see if subjects' cholesterol levels lower on average after the diet. So I did mu d equals 0 as the null, and the alternate statement, since it said lower after the diet, I used less than, because if it's lower, when you subtract, you would get a negative number if you subtract a lower number minus a bigger number. Now, I put in L1 is before and L2 is after. We want to know if the average after is lower. So I did the after L2 minus the before for my L3, and I got p-value of 0.0130, which is less than 0.05, so we rejected the null, and that means that we have enough evidence to conclude that the subject's cholesterol levels are lower on average after the diet. All right, on to example 5. Dominant hand. 5 players think they can throw the same distance with the dominant hand throwing and offhand catching hand. Conduct a hypothesis test to determine whether the mean difference in differences between the dominant and offhand is significant. So for this one, you want to see if there's a difference. Is there a difference? Okay, so pause the video and come back when you're ready to see what the answer is. Okay, so I put mu d equals 0, and because we're trying to see if there is a difference, I put mu d is not equal to 0, because if it's not equal to 0, that means there is a difference. I put dominant hand in as L1 and offhand as L2. Now what's nice about this one, because you're trying to see if they're not equal to 0, you can either do L1 minus L2 or L2 minus L1 for L3. Either one, it won't matter. Either way, you get 0.0230 as your p-value, which is less than 0.05, so you're going to reject the null, which means there is enough evidence to conclude the mean difference in distances between the dominant and offhand is significant. Okay, so we're going to move on to confidence intervals for 2 population means and actually 2 population proportions as well. So we talked about hypothesis testing for 2 samples. So now we're going to calculate confidence intervals for the 2 samples in the 2 populations as well. Because there are populations, we're not actually estimating the parameters for either population. So back when we did confidence intervals originally, it was for 1 population, and we estimated that the mean fell somewhere between 2.1 and 2.8, something like that. But we're not estimating the actual mean here, because there's 2 populations, and we're going to have 1 confidence interval, so you can't say that the 2 means are between 2 numbers. That doesn't make a whole lot of sense. So because we want to, what we're going to do is we're not finding the confidence interval to estimate either one of the means. We're finding the confidence interval to estimate the differences in the means. So the 3 confidence intervals that we're going to be learning is the 2 sample t interval. This is what you're going to do when you're estimating the difference in 2 population means that are not paired. And you're going to do a 2 prop z interval when you're estimating the difference in 2 population proportions. And then you'll do a t interval if you're estimating the difference for paired data. Make sure you use the data option. All 3 of these are very similar to when we did the test. It's just you're choosing interval instead. What's really nice is if you run the test first and then run the confidence interval to see if it matches, the data for the confidence interval will already be filled in because you had previously filled it in for the test. That part's really nice for our calculators to do for us. So for the interpretation, instead of saying we are 95% confident that the mean falls between these two numbers, we're going to say we're 95% confident that the difference in the means or the difference in the proportions is between, and then give the two numbers. Now another thing, now before we were estimating where the mean fell. Where was the mean? Where was the proportion? We could see whether or not the mean was greater than 20 or less than 20, or whether 20 fell within the confidence interval. But here, we're talking about differences. So where should the differences fall? So this is kind of what it tells us. So really, although we're interested in the numbers for the confidence interval purpose, when we're trying to figure out what the confidence interval is showing us, really all we need to look at is the signs. So think about this. We're finding the confidence interval for the differences in the data. So if the difference, when you subtract, let's say, the two means and you get a positive number, so if our whole confidence interval is positive, that implies that the first number is bigger than the second number. It implies that the first mean is greater than the second mean, or that the first proportion is greater than the second proportion, or that mu d is greater than 0. If you have two negatives, when you subtract and you get a negative number, that means the first number was smaller than the second. So it implies that mu1 is less than mu2, or p1 is less than p2, or that mu d is less than 0. And if you get both a negative and a positive, that implies that 0 is included. And if 0 is included when you subtract two numbers and you get 0, that implies that there is no difference. So it implies that mu1 is equal to mu2. Or that p1 is equal to p2, or mu d is greater than, mu d is equal to 0. Okay, look at example 1 for confidence intervals, blood pressure. A drug company has developed a new drug that is designed to reduce high blood pressure. To test the drug, a sample of 15 patients is recruited to take the drug. Their systolic blood pressures are reduced by an average of 28.3 millimeters with a standard deviation of 12.0 millimeters. In addition, another sample of 20 patients takes the standard drug. The blood pressures in this group are reduced on average by 17.1 millimeters with a standard deviation of 9.0 millimeters. Assume the blood pressure reductions are approximately normally distributed. Find the 95% confidence interval for the difference between the population mean reduction for the new drug and that of the standard drug. So we're finding a confidence interval, and we have two samples from two different populations that we're dealing with, and they're talking about means and standard deviations. So we're going to do a two-sample t interval. Okay. So when we do a two-sample t interval, it's going to ask us for x bar 1, sx1, and n1. And it's going to ask us for x bar 2, sx2, and n2. And then it'll ask us for our confidence level. So let's fill those in. So, it doesn't really matter which one is which, really, I guess. Not in this case, anyway. We're trying to see if the confidence interval for the difference between the population mean reduction for the new drug and that of the standard drug. And what did they give us first? It says, to test the drug, a sample of 15 patients is recruited to take the new drug. So, new drug is first, and then the standard drug is second. So x bar 1, we had 15 patients, so that's the n, and their average x bar 1 is 28.3 with a standard deviation of 12. And then for x bar 2 for the standard drug, that was 20 patients, so I'm going to go ahead and fill in n2 for 20 patients. Their mean was 17.1 with a standard deviation of 9. Or 9.0. The confidence level is 95%. Okay, so I'm going to pull up the calculator. All right, so stat, I'll turn it on first, stat, test, we want a 2 sample t interval. So that is, for mine, 2 sample t interval is 0. You want to check your calculator and see what number that falls on. We want to choose stats because they gave us statistics. X bar 1 was 28.3, SX1 was 12.0, N1 was 15, X bar 2 is 17.1, SX2 is 9.0, and N2 was 20. And then our confidence level is 0.95. Pooled, choose no. And we get 3.5912 to 18.809. So one way you can write it is in interval notation, 3.59, 18.81. Another way to do it is you can say 3.59 is less than the mean of the new drug minus the mean of the standard drug, which is less than 18.81. We used to just have the 2 on either side and mu in the middle, but now you have to have the difference in the middle. And we would interpret it by saying we are 95% confident the difference between the population mean reduction for the new drug and that of the standard drug is between 3.59 and 18.81 millimeters. Okay, so also what can this tell us? Because they're both positive, this implies that mu1, or the mean of the new drug, is greater than the mean of the standard drug. So it shows that there definitely is a difference. Okay. In a study, example 2, in a study of the effect of air pollution on lung function, a random sample of 50 children living in a community with a high level of ozone pollution had their lung capacities measured, and 14 of them had capacities that were below normal for their size. A second random sample of 80 children was drawn from a community with a low level of ozone pollution, and 12 of them had lung capacities that were below normal for their size. Construct a 95% confidence interval for the difference between the proportions of children with diminished lung capacities between the two communities. And it looks like there was an extra word in there. Anyway, so this proportions, this is going to be a 2 prop z interval. So why don't you pause the video and see if you can come up with the confidence interval and figure out the interpretation and what it tells us. Okay, we did a 2 prop z interval with this data put into the calculator and got negative 0.017 to 0.277. You can also write it this way. So we're 95% confident the difference between the proportions of children with diminished lung capacity between the two communities is between negative 0.17 and 0.277. Now, because that one is negative and one is positive, this implies that P1 equals P2, or that there is no difference. That's what it implies. All right, so one more. Suppose we select 16 volunteers that are given a test in which they had to push a button in response to the appearance of an image on the screen. Their reaction times are measured. Then the subjects consumed enough alcohol to raise their blood alcohol level to 0.05%. They then took the reaction test again. Calculate a 95% confidence interval to estimate the mean difference in reaction times. This is paired data. So we're doing a t interval. So L1, L2, and then remember L1 minus L2 for L3, and then run your t interval. So pause the video and come back to see if you got it. Okay, for L3, I did L1 minus L2, the after minus the before. So we're 95% confident the mean reaction times is between 1.207 and 11.793. And I missed a word here that should say the difference in reaction times. And because they're both positive, it implies that the mean difference is greater than 0. All right, that's it. Let me know if you have questions.